The morning of August 12, 1940 broke with a kind of tension that made even veteran pilots uneasy. Over the gray skies above Hornchurch, squadron leader Brian Lane coasted his damaged Spitfire home, 3 bullet holes stitched across the tail and a frustration far deeper than metal scars. Moments earlier, he'd had a Messerschmitt Bf 109 locked perfectly in his gun sight, close enough to see the outline of the German pilot's helmet. Lane pressed the firing button, expecting the brutal punch of his new 20mm Hispano cannons. Instead, 3 shots. Then silence. The cannons froze mid-burst, leaving only the lighter Brownings chattering uselessly against German armor. The 109 simply rolled away, untouched, vanishing into cloud as if mocking him. Lane wasn't alone. All summer, RAF pilots returned with the same bitter report. Britain's new cannon-armed Spitfires were failing exactly when they mattered most. The Air Ministry had rushed these Hispano Mk2 cannons into the Spitfire MkII to counter Germany's tougher bombers with armored fuel tanks and self-sealing skins. A single explosive shell could do what hundreds of rifle-caliber bullets couldn't. But in real combat, between June and September 1940, No. 19 Squadron logged cannon stoppages in over 60% of engagements. Some guns jammed after 5 rounds, others after 30. Once jammed, the cannons became dead weight, and the RAF desperately needed every ounce of firepower. The investigation revealed a nightmare list of flaws. The 60-round drum sat sideways in the thin Spitfire wing, never designed for such a weapon. High G turns disrupted the feed system. Ammunition came from multiple contractors with inconsistent dimensions. Springs stiffened in freezing altitude air. Recoil sometimes snapped internal mounts entirely. It was a weapon engineered for French thick-wing fighters, now crammed into one of the slimmest wings in the sky. By October 1940, most cannon-armed Spitfires were quietly pulled from frontline service. Pilots mourned the loss, not of the flawed guns, but of the incredible stopping power they glimpsed on the rare occasions the cannons worked. Some had watched a single burst shear through a Heinkel's wing like paper. Meanwhile, across the Channel, the Luftwaffe was studying every scrap of this failure. Captured Spitfires and interrogated British pilots painted a clear picture. The Hispano installation was unreliable to the point of irrelevance. German intelligence concluded, if a British pilot fired his cannons during the first pass and you survived it, the rest of the fight belonged to you. By early 1941, Luftwaffe doctrine shifted. Messerschmitt pilots were taught to exploit vertical maneuvers, knowing British fighters hesitated to fire until dangerously close. German bombers loosened their formations, trusting that RAF machine guns alone couldn't kill them quickly. Their assumptions were logical. Their intelligence was accurate. And it was also about to become fatally outdated. Because while German planners congratulated themselves on understanding the Hispano's flaws, British engineers were already tearing the weapon apart, rebuilding it, and solving every single problem under the pressure of national survival. Germany had prepared for yesterday's RAF, even as tomorrow's RAF was quietly taking shape in workshops across the Midlands. And at the center of that transformation was a man who had never meant to design weapons at all. Marc Burkigt, the gifted Spanish-Swiss engineer whose luxury V-12 engines once powered Europe's finest automobiles, and later the legendary SPAD fighters of 1918. In the 1930s, France approached him with a new challenge. Build a cannon powerful enough to tear apart the modern, armored bombers rising on the horizon. He had no idea his creation would soon decide the fate of the skies over Britain. Burkigt accepted the challenge, setting up his design bureau in Geneva, determined not to scale up old machine gun concepts, but to build a true aircraft cannon from the ground up. Most weapons of the era simply enlarged rifle caliber systems, keeping the same basic mechanics. Burkigt knew that path led only to limitations. A 20mm cannon firing explosive shells at 600 revolutions per minute faced stresses totally unlike any machine gun. The weapon had to survive massive chamber pressures and manage recoil forces that could tear lesser designs apart. For 18 intense months, he developed a gas-operated system using a piston beneath the barrel. As each shot fired, propellant gas vented through a port, driving the piston rearward to cycle the bolt, eject the spent case, and feed the next round. But Burkigt's brilliance lay not in the mechanics alone. He engineered the entire weapon as a single integrated system. A cooling jacket that directed airflow to prevent overheating. A pneumatic buffer stabilizing the rate of fire. a precisely machined chamber with flawless headspace to avoid ruptured cases. By 1935, the prototype HS.404 fired 400 rounds without a single stoppage during trials at Villacoublay. France immediately ordered mass production, fitting the cannon into Morane-Saulnier and WWII fighters. British observers were impressed and secured a license to build the gun at a new factory in Grantham, designating it Hispano MkII. On paper, it was devastating. 840 meters per second muzzle velocity, nearly 1 kilometer effective range, and shells carrying twice the explosive charge of German 20mm rounds. A 2-second burst could rip apart bomber wings or smash through armor machine guns couldn't touch. But the moment the weapon met the thin, elegant wings of the Spitfire, Berkigt's carefully balanced system unraveled. His design assumed deep French wing roots that could house the 60-round drum horizontally. In the Spitfire, British engineers had to cant the drum at awkward angles Berkigt had never tested. The French-style hand-tuned springs were replaced by mass-production parts. And British ammunition, supplied by multiple factories, lacked the micro-precision Berkigt expected. The result: the cannon that ran flawlessly in French service became unreliable in British hands. Not because of bad engineering, but because Britain had installed it under entirely different conditions than it was built for. The failures of the Hispano MkII were not design flaws, they were implementation flaws wearing a clever disguise. The breakthrough came from an unexpected source. Joseph Szydlowski, a Hungarian engineer who had fled Europe in 1939, arrived in Britain with 20 years of experience manufacturing Hispanos under license. He understood exactly what Berkigt had intended, and exactly what the British needed instead. In February 1941, the Air Ministry handed him a daunting mandate: redesign the weapon from scratch. Reliability above 95%. No excuses. Szydlowski's team soon identified the worst offender: the 60-round drum magazine. Its spring system weakened unpredictably under G-forces, and once empty, the pilot had no way to reload. The solution was obvious but brutally complex. Replace the drum with a belt feed system. Machine guns had used belts reliably for decades, but scaling the idea for heavy 20mm rounds required designing new feed units, rollers, and guides capable of aligning each huge cartridge perfectly at high speed. 7 months of continuous redesign produced the answer: a robust belt feed unit holding up to 120 rounds, strengthened extractor and reinforced barrel mounts, a recoil buffer tuned for freezing altitudes, a chamber engineered to accept British ammunition with its slight dimensional variations, a harder, stronger firing pin to ignite inconsistent primers. These were not elegant solutions, but they were practical, and they worked. By August 1941, the first Hispano Mk2 cannons reached frontline RAF squadrons. Installed in the Spitfire MkVB, they transformed air combat overnight. On August 23, Flight Lieutenant Alan Deere fired over 400 rounds in a single mission without a single jam, shooting down 2 Bf-109 in the process. Within weeks, units reported stoppage rates below 5%, most caused by damaged ammunition rather than the weapon itself. Britain finally had the reliable cannon it had needed since 1940, and German intelligence had no idea. By March 1942, the ultimate proving ground appeared: Malta. The island endured relentless Axis bombardment, more intense than even the Blitz. Spitfire VC squadrons led by squadron leader Edward "Jumbo" Gracie arrived with aircraft carrying 4 Hispano Mk2 cannons, double the armament of earlier fighters. Conditions were brutal. Dust invaded every mechanism. Salt air corroded metal overnight. Temperatures swung from freezing dawn scrambles to 50 degrees Celsius cockpit heat by afternoon. Pilots flew 4 to 5 sorties per day against raids of 50 to 100 enemy aircraft. Ground crews rearmed fighters in rock-cut blast pens under constant bombing. If the Mk2 had any weakness, Malta would expose it. During the week of 16 to 22 March alone, Gracie's pilots intercepted 17 incoming raids, firing more than 14,000 rounds of 20mm ammunition as the island fought for survival. And the results of that brutal week began showing up immediately in the squadron's war diary. It listed 11 stoppages, but inspections revealed that 9 were caused by damaged ammunition, dented cases from rushed belt loading or cracked propellant from rough handling. Only 2 were genuine weapon malfunctions, both traced to broken feed pawls that armorers replaced in under 20 minutes. Even under Malta's punishing conditions, the Hispano Mk2 was achieving over 94% reliability, a rate the old MkII could never have approached. One incident on March 29th made the improvement unmistakable. Flight Lieutenant James McLaughlin, flying with an artificial left arm after losing the original over Malta the previous year, intercepted a formation of Ju-88s with MC.202 escorts at 7,000 meters. Instead of closing to the short ranges machine gun-armed Spitfires required, McLaughlin opened fire at 600 meters, sending precise 3-second bursts through the bomber formation. 2 Ju-88s fell away trailing smoke before the Italian fighters could intervene. His gun camera showed shells detonating exactly where his gun sight placed them. He used only 90 rounds per kill, compared to the 300 to 500 rounds machine gun Spitfires typically needed. In Malta, where every shell arrived by convoy through Axis attacks, that efficiency truly mattered. By April and May, maintenance logs showed the Mk2 averaging over 2,000 rounds between stoppages, with most failures occurring only after components exceeded their expected service life. Sergeant Armorer Bill Hayden noted he could service 4 cannons in the time 2 MkII drums once required. The belt feed system simplicity meant fewer parts, quicker inspections, and faster turnarounds. Pilots grew increasingly confident taking long-range or high-deflection shots, knowing their weapons would fire exactly when needed. By June, as Malta's ordeal finally eased, the island Spitfires had proven beyond doubt that the Hispano Mk2 was reliable under the harshest operational conditions in the European theater. The only question now was whether German planning would adjust before that reliability cost them even more. On June 14, 1942, Oberleutnant Johannes Mackie Steinhoff learned the answer the hard way. Over the Pas-de-Calais, he broke left as tracers whipped past his canopy, assuming the distant Spitfire was firing desperately from far outside machine gun range. He rolled inverted to counterattack, expecting the British pilot to close for a proper firing pass. Instead, his Bf-109 FS tail section exploded as a sustained stream of 20mm shells tore through the fuselage. The cannon fire didn't sputter out after a few rounds, as German intelligence had insisted it would. It continued in a solid burst that sliced through his aircraft like a cutting torch. Steinhoff bailed out at 400 meters and spent the rest of the war recovering in a British hospital, one of the first to experience what intelligence reports had failed to foresee. He was not alone. Luftwaffe loss reports from May-June 1942 showed a disturbing pattern. British fighters were destroying German aircraft with accurate cannon fire at ranges previously considered safe. JG-26 alone lost 11 pilots over the Channel during those 2 months. Survivors consistently reported that British cannon bursts now lasted 5 to 8 seconds, a complete contradiction of earlier German intelligence assessments. Yet the intelligence system reacted slowly. Commanders had built doctrine around the assumption that British cannons would jam early, and institutional inertia made revising those beliefs difficult. When General der Jagdflieger Adolf Galland finally received a full analysis in July 1942, the findings were unequivocal. Engineers examining wreckage from 8 downed Spitfires found belt-fed Mk2 cannons, eliminating the MkI's drum feed failures. British ammunition with far tighter tolerances than before. No signs of the chronic jamming that German reports were still expecting. A near-intact Mk2 recovered near Abbeville fired 420 consecutive rounds during testing by German technicians. Galland immediately grasped the implications. German pilots had been trained to exploit assumed British weapon unreliability, accept the initial risk, then strike once the cannons jammed. That doctrine was now fatally outdated. New tactical guidance required pilots to assume every Spitfire carried fully reliable cannon armament. Hit-and-run attacks using superior diving speed were emphasized, and bombers were ordered to tighten formations and increase escort ratios. These changes reduced operational flexibility but acknowledged the new reality. The revisions came too late to prevent heavy losses. From June to September 1942, Luftwaffe fighter units in France and the Low Countries suffered their worst casualty rates since the Battle of Britain, with British cannon fire responsible for about 40% of all fighter losses. Individual German pilots adapted through bitter experience, but the institutional belief that British cannon armament posed only a limited threat, once accurate, now lethally obsolete, had already cost the Luftwaffe irreplaceable veterans. The roots of the Mk2's success lay not in revolutionary ideas, but in principles any 19th-century engineer would have recognized: precision, integration, and a deep understanding of how moving parts behave under stress. The cannon's reliability stemmed from its tightly controlled gas operation cycle. When a round was fired, gas at nearly 3,800 kilograms per square centimeter bled through a port 170 millimeters ahead of the breech into a piston cylinder. The piston's rearward stroke, timed for the projectile's exit, unlocked the bolt, extracted the spent case, and ejected it, all in 0.02 seconds. The redesigned belt feed was the Mk2's most important improvement. As the bolt cycled rearward, it pulled the belt laterally across the receiver. Each round, held in fabric pockets stiffened with brass clips, was stripped and guided downward into alignment with the chamber. Even a 2 mm misalignment could cause a jam or dangerous rupture, so the feedway and guide rails were machined to extreme precision. On the forward stroke, the compressed piston spring drove the bolt ahead, seating the round and locking it into battery. An electrical solenoid released the hammer the moment the pilot pressed the firing button. The entire cycle repeated every 0.1 seconds, producing the cannon's 600 revolutions per minute rate of fire. Heat management remained critical. Each shot produced immense thermal load, and sustained bursts could push barrel temperatures towards 700 degrees Celsius in under half a minute. Yet the Mk2's cooling design, airflow integration, and steel treatment kept the weapon functioning through the punishing, continuous engagements demanded by Malta. At such temperatures, steel rapidly loses hardness, and barrels can fail. To prevent this, the Mk2 used a cooling sleeve that directed fast-moving air around the barrel in a spiral path. At a Spitfire's usual 500 km/h combat speed, this airflow kept temperatures below 400 degrees Celsius even during full-length bursts. The design work was invisible to pilots, but absolutely essential. Chamber dimensions had to remain stable, or even slight thermal expansion could disrupt feeding and head spacing. The result was simple. The cannon's advertised 600 round per minute rate wasn't theoretical. Pilots could rely on it in combat. That reliability mattered on June 6, 1944, when Flight Lieutenant Pierre Clostermann circled above Normandy at 3,000 m. His Spitfire 9 carried 4 Hispano Mk2 cannons with 120 rounds each. Their mission was clear: stop German armor before it reached the beaches. The first target was a column of Panzer V tanks moving toward Sword Beach. Clostermann dived, lined up at 400 m, and fired. A 3-second burst sent armor-piercing and high-explosive rounds across the lead tank's upper surfaces, disabling it almost immediately. Pulling up through smoke and returning for another pass, he saw that all 4 cannons had functioned without a single hesitation. That pattern repeated all day. Spitfires ranged across the invasion corridor, destroying trucks, armored cars, artillery sites, and fortified positions. Against these targets, machine guns would have been nearly useless. A 2-second cannon burst delivered roughly 40 shells, enough to tear open vehicles, collapse light structures, or ignite ammunition stores. Pilots discovered they could drop bridges by focusing fire on structural points or detonate ammo dumps that machine guns couldn't set off. One pilot, Johnny Johnson, eliminated 4 trucks and an ammunition carrier in a single run, using only 200 rounds. Normandy's tempo was brutal. Aircraft flew 5 or 6 sorties a day. Ground crews rearmed them in open fields under fire. Engines stayed running while belts were loaded. Cannons often fired over 1,000 rounds per aircraft per day. Yet June-July maintenance logs from 2nd TAF showed stoppage rates under 6%, and most were caused by battle damage, not mechanical faults. The Mk2 was absorbing punishment far beyond anything pre-war testing had imagined. This reliability also reshaped German expectations. Their defensive planning assumed that Allied fighters relied mainly on rockets and bombs. Cannon fire was expected to be secondary. Instead, German units reported that Allied fighters were destroying armored vehicles and defensive positions with cannon fire alone, and doing so consistently. Movement during daylight became nearly impossible anywhere within 50 kilometers of the front. When Allied aircraft appeared, their firepower was instantly decisive. The Hispano Mk2's 600 round per minute capability wasn't just a number on a blueprint. It directly influenced the pace and outcomes of ground fighting. And this performance validated every hour spent turning a flawed early design into one of the war's most dependable aircraft weapons. Its influence didn't end with the war. When Air Vice Marshal Harry Broadhurst inspected captured German airfields in 1945, he found that late-war Luftwaffe weapons attempted to match the Hispano's reliability but never fully succeeded. The MG-1 had adopted belt feed concepts, yet poor wartime ammunition quality kept its performance inconsistent. Japan's Type 99, derived from an early Hispano export version, also struggled with feed issues in the Pacific. By contrast, the Hispano Mk2 became a global standard. By 1948, more than 30 nations fielded Hispano-armed aircraft. Rebuilt European air forces installed it in their new fighters, and even former Axis nations adopted it under Allied supervision. Japan's new Air Force equipped American-supplied F-86 Sabres with improved Hispano MkII cannons. Israel used Hispano-armed Spitfires and captured Bf-109s during the 1948 war. Development continued. The MkII appeared in 1947 with higher firing rates, 850 revolutions per minute, and reduced weight. RAF Hunters and Swifts carried it into the 1950s and 60s, and reports from Suez and the Malayan emergency confirmed stoppages remained extremely rare. Pilots noted that jet speeds improved cooling and feeding even more. The final evolution came with the 30mm Aden cannon, developed in the early 1950s. It used a revolver-style action to reach rates over 1,300 revolutions per minute while keeping the Hispano's core principles: robust belt feed, gas operation, and strict ammunition compatibility. Its designer, Roden Smith, had maintained Hispano cannons during the war and built those lessons directly into the new weapon. In many ways, the Aden was the Hispano's natural successor. Mark Burkett, the engineer behind the original concept, died in 1953, known more for his automotive work than his influence on air combat. But his design, refined into the Mk2 and eventually into the Aden, shaped aerial warfare for decades. Aircraft from more than 40 countries would carry weapons descended from his early ideas. What German intelligence once dismissed as unreliable became the benchmark others tried to reach. And at the heart of its legacy was one simple fact: when the moment came, it fired, every time. That reliability turned outdated assumptions into fatal errors, gave pilots the confidence to fight aggressively, and proved that even a troubled design could become a defining success through pure engineering discipline.